outer space there. This diagram, right? What are you asking? Okay. Well, that's a good question, actually. This is complicated. So, first of all, now this is taking place in my mind. Okay? The overall reaction. This is what we've done so far. We have tank electrolysis, and we've gone from glucose to iron. So the next step is the oxygen available to that it enters this cycle, not a cycle, but a series of reactions. So this is the pyruvate oxidase complex or the pyruvate dehydrogenase complex. Either one is fine. So the overall reaction is pyruvate, coenzymations in the group which is acid OA and ADH, proton CO2. Okay? And you need the both, the folic acid involved, magnesium, FAD, and cyanide pyrophosphate. So the first step is the first enzyme, which is actually pyruvate dehydrogenase. Pyruvate dehydrogenase. And that's P1. P1 is pyruvate dehydrogenase. It has the test is cyanide pyrophosphate. You know, if you write negative, you can write it all out of negative responses. And so this is my simple. And you can sort of follow what's going on. So, our rate reaction releases this CO2 that goes up to there. Now, what's left over is a 2-carbon unit. 2-carbon unit. Now, we want to get the energy out of that. So, the second enzyme comes along. That is dihydrolycoyl transacetylase. Mouthful. And so what happens is dihydrolycoyl means that's what dihydrolycoyl. Transacetylase, we're going to transfer an acetyl group. So does that actually happen? So here is the enzyme from the previous step with a 2-carbon unit, and it passes on the acetyl group to what would be sulfur. You see that? So this acetyl group is transferred by this enzyme, this transacetylase. Okay, so this acetyl group is transferred to sulfur. There it is. Sulfur now has acetyl. And one of the, so this bond is broken here. Cyclic sulfur, that sulfide bond is broken. And one of the S's now is reduced. Okay? And then, now the next step is this acetyl group is transferred to coenzyme. This is where the transacetylase comes from. Right? We're just transferring an acetyl group to something else, and as a result, we make acetyl-CoA. Why do we want to make acetyl-CoA? Because that's what we indicated in the peptide. So, now the lipoyl is now dihydrolycoyl. This is what is meant by dihydrolycoyl. We have two SHs next to each other. But they are, because they are reduced, they contain energy. And the next step is to get the energy out of those SHs. Okay? So that brings in the third enzyme. The third enzyme is called dihydrolycoyl dehydrogenase. So we know it's an oxidation reduction. So the hydrogen is here from the sulfur. This hydrogen and transferred to FAD. So E3 is this enzyme, dihydrolycoyl dehydrogenase. So these are two hydrogens, and they both transfer to the FAD, and now you get E3 and E2. Meanwhile, you regenerated this thing. Let's go back up here. get those hydrogens off. Because they have a bit of energy. So the hydrogens are going to be transferred to NAD as a hydride ion. Hydride ion. You make NADH and you regenerate these three. So when you add this all up, what's happened? We have made CO2. We have made potassium chloride. And we have made NADH, which is what's happening in the overall reaction. Right? We made potassium chloride, NADH, proton, and CO2. So remember, we are also interested in where the carbon dioxide is coming off. So it's this step here where the first carbon go off of CO2. We start with 6 carbons, right? That's where we go. We broke it down to 2 3-carbon units. So we're looking at the 3-carbon unit here, and one of them now is the CO2. So we multiply that times 2. The fact is from glucose is 6 from the chloride. The 2 carbon is down. Now the other important thing about this transport is that this enzyme here, and where oxygenate binds to use a thing called the carbon. So this is bad news. You're poisoned by arsenic. This is bad because this is a crucial enzymatic step. Why is it crucial? Because it allows you to get into the cycle. If you don't get into the cycle, you can actually run off the cycle and make lots of good use. So then you have to look, you'll be living on tablets of color. That's all you have. You will make a lot of ATP. This is reversible. This is reversible. How would you reverse that? Those SHs and found what would you add? The compound with 2 SHs, that's the compound. Right. That's what the antidote. Any compound that has carbon next to a carbon with an SH is going to do the trick. So anything which has this structure is the antidote. Why is that? Because if you add a lot of this, by mass action, you're going to push the oxygenate off that compound. Make sense? Well, anyway, that's the antidote. So if you have arsenic poison, so we should really understand what arsenic does relative to arsenate. That I would feel high probability. What is arsenate? Talk about that. Arsenate is in a couple of substrate level concentrations. What that actually means, let me go back to this. So the difference between arsenite and arsenite, which is reacting with the SH2 to form a compound, the arsenate is in glycolysis. This is the step. You glycerol by 3-phosphate, the hydrogenase step. So when we talk about glycerol by 3-phosphate dehydrogenase, this was the overall reaction. So acetaldehyde and glycerol by 3-phosphate is reacted with NAD. You make this compound C-double bond O phosphate. Okay? But if we add arsenate uses the PR total, PR table very close to phosphate. So the arsenate gets in, instead of being a phosphate, you add an arsenate here. The arsenate gets in and you get this compound. This is unstable. The phosphate one is stable. The arsenate one is not. And it breaks down directly to 3-phosphoglycerol. Okay? So it eliminates this step here. It eliminates this important is because now we don't have this step, we can't make it. Why is that bad? Because, remember, in the first part of glycolysis, we use the 2 ATPs. Right? The net process of glycolysis was supposed to make 2 ATPs overall, right? Here, this step is eliminated because you go directly. Just look at this now. Instead of going to this, we're going directly to this. This is this. And you don't get anything. So, the 2 you put in, we don't get anything back. And then the 2 we get at the very end of glycolysis, this means that you put in 2, you get 2 out, but it's no net ATP. Got it? Okay, so next question. Next question, yes. Cancer cells have a high rate of glycolysis. And why is that? Because when cancer cells are formed, there are multiple mutations. Not one mutation, multiple. So 7% of all cancers just put on one is found. So it's not all the cancers, but those 70% of this occur. There is no oxidative phosphorylation. In other words, this step is wiped out. This thing, there's nothing going on. Can't make ATP from this. This is where we're going to make all the ATP. So this is the foot. So, in order for the cancer cell to grow, we've got to get ATP from somewhere. So this turns on glycolysis at a much higher rate. And it makes those 2 ATPs the times many-fold higher. And why is that important? Because if you develop a study, you have this. This technique here, this is quite a big deal. The PET CT. This is all based on Warburg observation. So the PET scan is, well, if you are diagnosed with a cancer, you have to know what stage it is. You need to know, is that the primary cancer? Have you gone anywhere else? So the treatment changes, you've gone somewhere else. So this technique is where they give you a form of glucose, which is radioactive, but not metabolized. Now what they're looking at is that those cancer cells which have a higher rate of glycolysis also will uptake more glucose at the same time. So they give you this stuff for an hour or so, and then you do a CT scan for it. You want to identify what the organs are, and then you measure the radioactivity from the radioactive form of glucose, and wherever the cancer is, you will localize, and it will come up as a thing like this, and then you know. Okay, it's only here, it's not anywhere else. Okay, now we know what to do. Remember, the FDA, the Federal Drug Administration, has approved a whole bunch of protocols how to treat each kind of cancer. And these protocols work. They don't work, otherwise they can be approved. They work on each cancer, and then you go back and look at it, and see what works. You're all set. Any questions? Okay, so that was only one name, right? You wanted more. How about dancing? What is dancing? He discovered insulin. It's not a trivial thing. One of the really great discoveries in medicine. Where is dancing located? Toronto, in Canada. Anybody visit Canada here? Yeah, nice country, right? Great friendly people. What California? You don't have to. Okay, so what else do we have? Water, banking, credit. Credit. Credit was responsible for the price on the acid factors. And he was at Oxford University at the end. So, yeah, that's sort of funny. Professor Coe was this guy who interviewed the first Dutch people that came from infectious disease with horrible symptoms. Now, maybe we should know that name. Very. These people were very, and were doing damage. It was very hard to walk. Very easy walking on the beach. The nervous system is screwed up and hard to screw up, and it's going to start too. So he interviewed those first Dutch sailors and army people, and he recorded it. So it was the first historical basis of this disease. And then he became really famous because of his painting. And if you go to Holland, if you go to this museum, this famous museum in The Hague, the capital of the Netherlands, which is also where he began the world forward. And so he paid Rembrandt money to be in his painting. It's called the Manly Lake. And that changed, acting very knowledgeable. First professor was added, and all the other people hanging around are also people that you say you think what they get very mortal, right? And this is a very famous thing. But so anyway, we should not only science but we should art. We want to be just boring about chemistry. Or boring physician. Or boring tech. Drawing your background. Okay, does that answer your question now? Is there anything?
Robert Manley from and you mentioned
Christian Eichmann, I'm sorry, you're actually right. That's important. Christian Eichmann was the guy that actually was much smarter than I am, obviously. Okay, Christian Eichmann was the guy that was sent to infectious disease. After 300 years, people got sick of not knowing what to do about the disease. They sent him, he was a physician. Most of the research that was done for biochemistry was done by physicians. So he went there to, which is now in the meeting together. He noted right away the white story. The white story was the natives were eating dry rice, they were healthy. These Dutchmen and ladies, they thought, they brought their white rice with the conviction that it was superior to the brown rice. And it turned out that the white rice was very poor. The outer coat of the rice, which contained all vitamins, was lost. So that was why they developed the disease. And Eichmann realized that, he postulated there was a factor there, vitamins, he identified the vitamins later. Yeah, thank you for pointing that out. Really good. Anything else I forgot to mention? You had your hand up. Okay.
I was wondering for your reaction on
Page 51?
yeah.
Every time page 51. Okay, now your question is, what does this have to do with anything? Okay, good question. What does this have to do with? Well, these reactions are taking, for example, trans-alkylase and trans-helix to show you that trans-helix is a type of compound that has unsaturated phosphate, and what it does is, this is where the accused pathway comes to begin. We've got a bunch of sugars hanging around. What should we do with that? And this is what we do. So here is cellulose triphosphate, residual phosphate. They don't seem like very exciting sugars. But if they interact with each other in the presence of trans-helix, that two-carbon unit is going to be moved and hooked onto this, and you get hooked up to the phosphate. On the other hand, what you have left then, you remove 5 from 2 is 3. And that's alkyne with other phosphate. So why are these important? Because both of these compounds are glycolytic intermediates. They can replace these compounds with their constituent side reactions. And transalkylase, that works the same way, but a little differently, because instead of 2 carbons, 3 carbons is transferred. Okay, so you start with second haploid phosphate, and this carbon phosphate is the alkyne receptor. So 3 goes on to 3, then gives you 6. That's hooked up to phosphate. Use another way of getting something useful from a second carbon sheet. Now this thing here, the residual phosphate, you probably go back up here and you have to do something like that. So in other words, these series of reactions are going to give rise to what's of interest to us is to give rise to glycolytic compounds. Those are the only ways the question would be asked. If you look at this and this, what do you get? If you have glycolytic intermediate at the end. All right? Does that answer your question? Next question. Actually, we have to move on. We have one more thing I need to talk about. And that is the first one. So we've already talked about the target oxidative complex. So here are a series of enzyme reactions. You need to know the criteria. You will not be asked to reverse the or a color. One reaction is not together. If there are 38, you know which one it is. That means the question of the reaction from factors dealt with you. Right? What about little things stuff? This is like learning the language. Okay, the first step is catalyzed by the enzyme citrate synthetase. There we want to call acetate, put the compound in the red cycle, and you get citrate. Citrate. Okay. This is the same citric acid that you would find in fruit. Take this away. So that's pretty easy, right? And it tells you citrate synthetase, so you're going to get citrate. You have to have 3 carbon silicates to make it work. Next thing that's important is a conative. Now there is an intermediate called cistoconative. We're not going to bother with that. So this compound here is conative. All that's happening here is that you're moving a hydroxyl group from carbon number 2 to carbon number 3. You can call this a nucleus. The name of conative is stuff. The other important thing about this enzyme is it has a 4 iron for sulfur at the active site. If you will use 1 iron, the enzyme is dead. It needs 4 iron for sulfur. Then we come to the main regulatory enzyme called the peptide. So we know you've got to know those 2 regulatory enzymes. You want glycolysis, what is it? Phosphocryptocapsid. Here it is isocitrate, the isocytrate. So both of these are allosteric enzymes, huge number of sectors. We have a positive effective site and a negative effective site. So ATP is the universal negative spectrum. High concentration basically is glycolysis. So it is a strength level. So let me know, right? ATP is again power potential. But how does that actually work? It's where if there's a high concentration ATP, it will diffuse back to this enzyme, and this enzyme will bind to the negative effective site, causing the enzyme to go to the inactive configuration. The enzyme no longer works, and then stops the process. On the other hand, if you have a lot, so as the ATP is consumed inside reactions, so this is going out in the cell, right? ATP, so this is got a phosphate, involved with all kinds of reactions, protein synthesis, muscle contraction, movement of bad reactions, good reactions, and so forth. And so high concentration ATP is diffused down to this enzyme and also the glycolysis, and it will attach to the positive vector. And then that means that the inactive enzyme goes to an active conservation. So this enzyme stops working, and that stops the whole drug cycle. Okay? Extending the line. Regulatory enzyme. Okay, now the next step is we have another complex of three enzymes, which we're not going to go into. These three enzymes are analogous to the pyruvate oxidase complex we found. Okay, so it contains pyrophosphate, adhesion, nucleic acid, SAB. What we're doing here is that we're taking alpha-ketoglutarate, NAD, and strolling and we're making succinylcholine. So the energy in this molecule is now transferred, part of it is transferred to NADH, and part of it is transferred to make the succinylcholine compound. This is the hydrogen compound. 3 steps involved. So guess what? That compound is also present. Something that looks like that is present in one of the reaction steps. So arsenite will also knock this out. It will knock out this entire step. Arsenite will knock out this entire step. Might want to note that. Okay, now the next step is we have this high energy bond here. We're going to break this bond, this carbon-sulfur bond. We're going to release a lot of energy. And that energy we're going to use to drive the synthesis of 1 ATP. Look at the fooling around here. And all we need to know is, as a result of this reaction, we make 1 ATP. Okay? So we've made, so far we have made NADH here, right? We made an ATP here. And actually the previous step we also made an NADH. Here we practice the NADH. So here is an NADH, step 3. This step, step 4, is another NADH. Why is it important to keep track of the NADH? And also the smell. So here, in this particular oxidase complex, we make an NADH, that's the second NADH. Now we have made another CO2. Okay? So remember, it takes times 2. So that 2 CO2 added to the previous CO2 is now 4 carbon CO2. We started with 6. Where are these 2 coming from? In this step right here is where we budgeting stuff. Let's just go back to step 3. Step 3 is making an NADH with making CO2. At this point, we have used up 4 carbons of the original group. In step 4, we get another NADH and use CO2. At this point, we have another 2 CO2s, so 2 plus 2 plus 2 is 6. All these carbons of this is gone. CO2. The energy that was in that molecule glucose is now stored in succinyl-CoA and NADH. Okay? So now in step 5, we break this bond here, the hydrogen sulfur bond, that releases energy, and that energy is used to make an ATP. This is the only part of the Krebs cycle where you make an ATP through substrate level phosphorylation. This ATP here is made through substrate level phosphorylation. Let me write this down. This ATP here is made, is the only example of substrate level phosphorylation in the Krebs cycle. The NADHs that we make are going to undergo oxidative phosphorylation at the membrane part. The FADH2 we're going to have in a minute is also going through electron transport chain, oxidative phosphorylation, and involved membrane. This is simply evolving substrate membrane. Okay, now this next step is more complicated because we have made succinate as a product. Here it is. And succinate has the CH2 and CH2. Although we cannot sense if they are different, the enzyme can. So this hydrogen and this hydrogen are different than this hydrogen and this hydrogen. So instead of removing hydrogen cis like this one and this one, we're already removing hydrogen cis. It's very specific. It passes those hydrogens on to UV-3O. So these also have double bond oxygen become used. And we make fumarate. Fumarate is trans-2-net body, not the six. And then what happens next is complicated. We just summarize and say that oxidative phosphorylation takes place and you make two ATP. That's the important part about this. You make two ATP. The next step is number 4. That's stereotypical. Step 7. So there is fumarate, trans-geometrical isomer. We have water crosses out the bond. We have that called fumarate. And now we have made another stereotype. We made L-beta. Not beta, but L-beta. The last step of the Krebs cycle is where we get maillate dehydrogenase. Maillate dehydrogenase. This hydrogen and this hydrogen are passed on to energy to make energy. So, the Krebs cycle, what it's done is we've got here the carbon and CO2 and made 3 NADHs, 1 SADH2, and 1 ATP. 3 NADHs, 1 SADH2, and 1 ATP. That's worth to us. That's worth to us eventually 12 ATPs, 2 CO2. So the Krebs cycle, as acetyl-CoA goes through the Krebs cycle, it produces eventually 12 ATPs, 12 ATPs, and 2 CO2. 12 ATPs. And how does that actually work? So there are 3 NADHs, right? Common 3 NADHs. We have 1 FADH2. And we have 1 ATP to substrate. Each NADH is worth 3 ATPs. That's times 3. You get 9 there. Each FADH2 is worth 2. And 1 ATP to the substrate level is 1. That's 12. So as each active CoA goes to the Krebs cycle, it doesn't happen. Within 3 NADHs, 1 FADH2, and 1 ATP, eventually those will yield 12 ATP. And we've got rid of the acetyl group as 2 CO2. That's the Krebs cycle. That's the whole point. Okay? Now there's some other stuff here that's not as important. So this calculation here is nothing that you have to worry about. It's just showing you how efficient is the process. It's about 70% efficient. The other 30%, the energy is not going to make it, it's going to make it heat. Heat our body much more. But the other reactions that we now encountering is aerobic combustion. Where have you seen that before? In gluconeogenesis. Gluconeogenesis. Here and here again. Guess what? Something that appears twice. That must have an Why is this step important? Because you have to realize that what started the Krebs cycle was the calorific. It ended up at the end. But what if there was no calorific? Krebs cycle can't work. No Krebs cycle, no oxidative oscillation. That's pretty bad news. So as soon as the acetyl-CoA builds up, it will act as a positive modulator in this enzyme and cause it to be stimulated. So it's going to strip out pyruvate directly and add CO2 and ATP to make it solid. That will then go back to the Krebs cycle to allow the Krebs cycle to work. Okay? The malic enzyme is not as important because it doesn't do the solid directly, but it's indirect. So again, the malic enzyme is not power density, so it's a separate reaction. It'll take pyruvate for CO2, will reduce the agent, and engage to malmalate and lead to heat. But it has to go one more step. The last step